Hey, welcome to episode 10 of my EE 101 series. Today I'm going to talk about resistance and Ohm's law. And this is a very important step when it comes to introducing circuit elements and circuit element behavior. Resistance and resistors are probably one of the most classical fundamental elements that you'll deal with, even in your most complicated circuits. And Ohm's law is the basis around all of the circuit analysis that you will perform on any circuit. Regardless of how complicated analysis techniques become, really most of them are all just based in Ohm's law. And this is something that, as an electrical engineer, this is essentially, this is the rule that you live by. Everything boils down to this. And so this is something that is very fundamental and important to understand. To jump right into it, first I want to talk about this idea of conductors and insulators. You might have heard these words before, and if you have any kind of knowledge of electronics, you know that conductors conduct electricity and insulators don't. And that's useful enough information for most people. But the truth is that there really is no such object or material in the universe that behaves like an insulator, or rather an ideal insulator. So really, it's not a question of if you're talking about a material, it's not a question of does it conduct electricity or not. It's a question of how well. And the answer to that question is resistance. It turns out that resistance is just another man-made concept. It has a relationship with voltage and current, and we use it as a measure of how well a material or a circuit element conducts electricity in the most fundamental sense. So let me explain that with a picture. Let's say you have a circuit element and you apply a voltage across it like this. Well, there will be some current that flows through it, like this. And we say, so let's say V and I. And the concept of resistance is just the relationship between this voltage and current. So say you applied a voltage across this circuit element, and then you observe the current. So you have a known voltage that you impose across the element, and then you measure whatever current flows through it. Well, then you would say, okay, this circuit element, let's say it's a resistor, and we represent a resistor with this symbol. So it's just this zigzag or this lightning bolt looking line here. And we would say that with that voltage and that current through it, and you'll label it, say, R, having some resistance, we say that the voltage and the current through this resistor, or this resistance, are related in this way. So V equals I times R. So what we're saying here is that the resistor, or the resistance, is this constant of proportionality with certain units that relates the voltage and the current. So resistance is related to material properties. And we use this symbol here to represent that material, this physical substance, that allows a voltage and current relationship in this way. One thing to note here is that in our experiment, I said that we applied a voltage and measured a current. Well, it works either way. You can apply a current and then measure the resulting voltage. In either case, there will be some relationship between the two. Right, as long as your circuit is not changing, as long as your circuit element is not changing, because it's just an object, right? Every time you apply a voltage, the same current will flow. And every time you apply a current, the same voltage will appear. And so that relationship between these two quantities, voltage and current, these two electrical properties, is the resistance. All it does is describe the relationship between the two. And this right here, this V equals IR, this is called Ohm's law. And yeah, like I said, It really is that simple. This is Ohm's law, right? It's three quantities related by a multiplication. And it's the basis for all circuit analysis you will ever do for the rest of your life. This is the most important thing to remember forever. As a professional industry electrical engineer, I can tell you that this is what I do on a daily basis. I mean, this is the root of it. And it does get, in application, you're applying it to vastly complicated circuits, but what it really boils down to is just this. And there are all kinds of corollaries that come from this as you apply Ohm's law to different circuit elements other than just simple resistors, and that's way down the line, but the point is, this is the basis for your entire reality, so master this. And so it's called Ohm's law. You might ask, what is the unit of resistance? Well, it's called an ohm. And so let's see, so we say that volts, remember volts, and I'm writing this as a unit relationship here, volts equals amps times ohms. So an ohm is a volt amp ratio. And the symbol for the ohm in units is represented by this Greek omega. Just like that. Just as the symbol for volts would be a little v, the symbol for amps would be a big A, and the unit symbol for an ohm is, again, this omega. A few more things to note here is, look at the way I drew this. I have the current flowing into the positive terminal of the voltage polarity. You can see I did that in both cases here. And if you remember what I talked about in a past video about the reference directions and polarities for voltages and currents as they relate to power, what this means is this is a passive device. So resistors consume power. They do not generate power. They're just circuit elements or physical materials that we use to close circuits or operate as specific elements in circuits. And there are many devices in the world that do specific things, but in effect can just be modeled as resistors. But the point being is, resistors do not source power. They only consume power. So you'll see this in this configuration where the current will flow into the positive terminal of a resistor. And also notice that based on all convention, except for very unusual cases, which will be discussed far down the line, but not in this basic discussion here, resistors, 99% of the time, you'll see these with positive resistance values. And like I said, there are cases where you can encounter a negative resistance in certain sophisticated circuits, but don't worry about that for now. For all intents and purposes, just assume that, and physically, resistance makes sense to talk about as a positive quantity. Another thing that I want to note is, so this is the way that I draw this symbol, and there's really only one other way you might see the symbol for resistance drawn, so let me write that out. So sometimes the exact number of zigzags or jags might be different. Some people draw a whole bunch of them, but the point is, when you see this sort of lightning bolt pattern or zigzag pattern, regardless of, regardless of how many people draw, this is the same thing as this. They're both resistors. And another interesting note is that in Europe, they often draw their resistance symbols actually just like this, as the generic circuit element symbol that I've been using. So, and this is actually fairly common to see if you're looking at circuit schematics online, or even certain textbooks will represent it this way. So just keep that in mind. When you see this, you might just be looking at a resistor. And also, as a note, just physically, if you've ever held a resistor that's been engineered for you to design circuits with, they kind of just look like this, where they're these cylinder shapes or rectangle shapes with wires sticking out of them, and they'll have labels and colors on them to indicate what they are. Another physical quantity you might hear discussed is conductance, and conductance and resistance are really just one and the same thing. They're just inverses of each other. So if I wrote, on the last page, I wrote Ohm's law in terms of voltage. So I said voltage equals current times resistance. And at the same time, you could say resistance equals voltage divided by current, or it's a volt-amp ratio. But what happens if you isolate current? So what you see is, so let me write this out, conductance. What you'll see is I equals 1 over R times V. And all we're doing here when we say conductance is that it's the inverse of resistance. So if we took this quantity, 1 over R, we could just write, and we'll usually do big G times V. And again, that equals I. So this is still just Ohm's law. In fact, this is the exact same equation I wrote on the previous page. We're just defining conductance to be 1 over R. And if you think about just the word, so conductance, right, it's the constant of proportionality for a circuit element or material that describes how well it conducts electricity, whereas its inverse, resistance, is the constant of proportionality that describes how well it doesn't conduct electricity. And so just remember that. So think about, it's in the name, resistance. So a resistor resists the flow of electrical current is probably the best way for you to think about it. Whereas a conductance will conduct electrical current. And so you can look at a circuit element from either perspective. You can just say, oh, it conducts this well, or it resists to this degree. And they're really, again, they're saying the same thing. And we say that conductances have the unit of inverse ohms. So you might see this, or sometimes we call this unit a Siemen, which is spelled like this, and abbreviated with a big S. All right, now let me talk a little bit about what a resistor is physically. It turns out that we can actually create fairly ideal resistances just by using the materials around us. And so what we do is, and when I say ideal, I mean it's we can create a circuit element, or we can take a material and it behaves as an ideal resistance because it doesn't have any parameters of other circuit elements that I will introduce, and also it consistently behaves as if it has the same resistance regardless of time or frequency that you apply to it. And I guess let me draw this out a little bit just to be a little bit more clear. So we'll take some material, it could be however conductive or resistive. We take some material, and this is probably a metal or some kind of ceramic, or there's many ways that we make resistors. We're very good at this, and we've been doing it for a long time as a society, or as a field of science and engineering. This is something we're very good at. And so we'll take, this could be copper, this could be aluminum, and then we literally will stick leads or wires to it, and we'll use it. So, this is conductive material, and then this is a circuit element. So I'm drawing a box around this just to show that. And then as the electrical engineer, as the circuit designer, you don't really need to know what's in this box, just that there's a certain resistance associated with it. And you can apply a voltage to these terminals and watch a current flow through it, or you can force a current through this element and watch a voltage appear. And so, physically what's happening here, if you think all the way back to when I talked about charge and current, you've got some metal, some conductor or some other material, and you're forcing a current through it. So you have these charges trying to flow through, and they're bumping into the lattice structure at the microscopic level to whatever this material is. And so these charges keep trying to flow and bumping into atoms, and then reaccelerating due to the force of the current or the voltage that's being sourced, and they keep crashing and reaccelerating and crashing and reaccelerating, which leads to an essentially constant, if you average across this entire material and look back up at a macroscopic level, an essentially average flow or an average velocity for these charge carriers. Then what you get is a constant current. So assuming you're applying a constant electromotive force or voltage, you see a constant current relative to this resistance. And so I know that I drew this squiggly line here, and you're probably wondering, how do we actually generate the resistance that we want based on what material we pick and what shape it's in, and I'll talk about that in just a second. So to make this easy, let me just talk about the case of a rectangular prism, or maybe a cylinder. I guess let me start like this. So let's assume, and this is a three-dimensional shape I'm trying to draw. I have this rectangular prism that looks something like this, and it has a height, a width, and a length. Now this resistor, or this object, this material here is some it's some material from our universe here on Earth. And to make it easy, let's just say it's all the same material. So it's either, let's pick aluminum, or it's copper. This is just a piece of metal that has some ability to conduct electricity, and it has these dimensions. So what we do is we say that, okay, so this, and we're going to say that this cross-hatched area that I'm drawing in here, so this height and this width make an area, and I'm going to say, and then there's this this area in the back here, I'm going to say that I'm trying to force current to flow with respect to the length. So I'm going to, if this was a circuit element, the leads would be here sticking out in this direction, and then I'm going to say that I'm applying a voltage across these two ends so that the current will flow along the length of this metal bar. And so first we're going to say that the height and the width, height times width, equals an area A. So there's a cross-sectional area with which the current is flowing through. The current, because it's flowing from this end to this end along the length, only has so much space it can flow through, and it's constrained by the width and the height are making this rectangular area, and it has to flow within that area for a certain length. So we say that the resistance of this metal bar is described by this formula, where this is the Greek letter rho, or I guess we could just say it looks like a P, but it's the Greek letter rho, and we have the length here. So resistance is rho times L divided by A, where the length is L, and A is this cross-sectional area that the current has to flow through. And rho, or this little p, is a parameter called resistivity, which is entirely related to the material that this is made of. And so, okay, how did we get here? Well, really, you might be asking, well, how do you know what the resistivity is? If it's different for every material, how do you measure it? And the answer to that is kind of tricky. So again, I talked about resistance being a man-made concept. I talked about us realizing, if you think about the physical process at play, like what happens when you apply a voltage and a current flows. So if you look at this relationship, we know that if we reduce the area with which current can flow, less current will flow. And if you increase the length that the current has to flow through, and think about what I just described about the charge carriers flowing at the microscopic level, the longer this distance is, the more each of those charges has to go through the lattice structure of these molecules and atoms. There's more collisions between particles, and it's more difficult for the current to flow. So we know intuitively that the longer this is, there will be a greater resistance to the flow of current, and the less area that the current has to flow, there will be a greater resistance to the flow of current. And so knowing these things, or knowing that this is how we want to define this property called resistance, which we as engineers have come up with as a tool to describe our circuit elements, well, then we can just say that we can measure the resistivity by creating this rule. So we can just take a metal bar of a certain length in a certain area, apply a voltage to it, measure the current through it, and then that tells us that material's resistivity. So I'm kind of really all these definitions are backwards, where I'm saying, oh, resistance is a function of resistivity, length, and area. It's, really we've defined resistance And so we know what voltage and current are, and let's say we have the ability to source these things and then measure voltages and currents. Well, then, of course we know how to make materials, and we can measure them and understand their dimensions. So as long as we have control over a voltage and a current, we can measure the resistivity of any material. And so then going forward, at this point, we know the resistivity of every material we'd ever want to use, and this is just the simple case of it's a single element, right? Say it's aluminum or it's copper, but you can have complicated scenarios with distributions of element densities and different elements, and then you can have vastly more complicated shapes than this. But what it boils down to is if you just understand. So this is a simple formula you might use to create a resistor. But all that really matters to you as the electrical engineer is knowing that if you have the ability to source and measure voltages and currents, you again can have any shape in here completely hidden away. You don't have to know anything about it, what it is, what it's specifically made of. You can just apply a voltage and measure a current, or apply a current and measure a voltage, and that will tell you the resistance of that thing. And that is a very powerful tool, and that's really how you're going to be using Ohm's law going forward. For completeness, I'm going to write this out. Resistivity rho has units of ohm meters, and you can see how that works out. Ohm meters. And just like we have this dual definition of resistance and conductance, and they're really one and the same thing, just inverses, you could also describe this material not in terms of its resistivity, but in terms of its conductivity. And conductivity is usually described with the symbol sigma, and the units are Siemens per meter. That's Siemens per meter. Okay, I think I'm going to end the video here. I really hope this was helpful, and let me know if there's anything else I can do to improve future videos. I think next time I'm going to talk a little bit about power consumption and calculations in resistors and resistances. I hope you have a great day.